Welcome, curious minds, to the deep dive. Have you ever paused to consider what really happens, in that invisible, seamless dance when you simply type www.google.com into your browser or hit send on a message?
It really does feel like magic, doesn't it? One second you're typing, the next, boom, the world's information.
Exactly. But behind that seemingly instant experience lies this intricate, really awe-inspiring ballet of rules, layers, and just countless interconnected devices all working together.
It's truly remarkable. And today, our mission, using your fantastic source material, is to peel back those layers. We're going deep into the foundations of computer networks.
We want to extract the key nuggets, connect the dots, and hopefully give you that aha moment.
Right. Whether you're prepping for a meeting, maybe catching up on the field, or just, super curious, our goal is to help you get truly well-informed. Not just the what, but the why and the how.
Because computer networks, let's be honest, can seem like this dense jungle of jargon, but that's why we're here. Think of us as your guides, yeah? Cutting through the tech speak to get to the fascinating stories, the surprising facts, the logic that makes the internet work.
And we'll definitely highlight the critical bits, the stuff that gives you that solid understanding you need to really grasp these concepts.
Okay, let's dive in. Where do we even start? What is a network?
Let's start right there. Simplest definition. A network is just computers connected together. Or devices, really.
That's it, just connecting things.
Pretty much, at its core. A group of devices that can talk to each other, share information, share resources, link two old PCs with a cable. That's a network. A tiny one, but still.
Okay, so how do we get from that, two computers and a cable, to the internet, some massive global thing?
Well, the internet is basically a giant collection of all those smaller networks. Think of it as a network of networks, spanning houses, cities, countries, continents.
And it's not just in the cloud, right? That's important. It's physical.
Absolutely crucial point. It's not some abstract concept floating out there. It's a vast, tangible infrastructure. Miles and miles of cables under the ground, under oceans, connecting everything. Physical wires.
So where did this all begin? The sources mention the Cold War.
Yeah, the genesis is fascinating. It really kicks off in the Cold War era, late 50s.
Yeah.
The U.S. government, feeling the pressure, creates ARPA, the Advanced Research Projects Agency.
To get a tech edge, right?
Exactly, foster breakthroughs. And ARPA had researchers spread out geographically. MIT, Stanford, UCLA, Utah were some of the first nodes.
So you have these brilliant people far apart working on sensitive stuff, and they need to share files, communicate securely, efficiently.
Precisely. It wasn't just convenience. It was a strategic need. How do you build a communication system that can survive potential disruptions, maybe even attacks?
That makes sense. And that led to ARP and DHCP.
Directly. In the late 60s, ARPANET was the precursor, the early internet. Initially military, then academic. The key idea was decentralization. No single point of failure. If one part went down, the rest could keep talking. A huge leap.
Okay, so you have these connected computers. How do they actually talk?
This is where protocols come in, isn't it?
Absolutely critical concept. Protocols. Imagine trying to have a conversation if we both had different grammar rules, different words for everything. Chaos, right?
Total chaos. Or building something complex. If every part manufacturer used different screw threads, nothing would fit.
Exactly. Protocols are those rules and regulations for data exchange. How data is formatted, sent, received, understood. They're the common language, the digital Rosetta Stone. Without them, it's just noise.
And it's not just one set of rules for everything.
No way. Different data needs different rules. Think secure bank transfers versus a video call.
Right. For the bank transfer, you need every single bit perfect. 100% accuracy. No errors allowed. Absolutely. But for that video call, maybe a tiny glitch, a dropped frame here or there, is acceptable if it means the overall conversation flows smoothly, without lag.
So you trade off perfect accuracy for speed sometimes, tailored rules.
Precisely. It's about optimizing for the specific application's needs. And these rules aren't just made up by one company. Organizations like the Internet Society, IEE, that's the Institute of Electrical and Electronics Engineers, and ISO, the International Organization for Standardization, they develop and maintain these standards.
How? Is it like a secret committee?
Not at all, actually. It's often quite open. Through processes like RFC's request for comments. Basically, someone proposes a new standard or an update, publishes it as an RFC, and invites the global tech community to review it, comment, suggest improvements. It's pretty collaborative.
Okay, so rules, collaboration leads to structure. And that brings us to network models, like the OSI model. Why layers? Why not just one big protocol?
Because networks are incredibly complex,
Mm.
just mind-bogglingly intricate. Layered models break this complexity down into smaller, manageable chunks, like building blocks.
Makes it easier to understand, maybe.
Definitely easier to understand, and crucially, it standardizes the interfaces between the layers. How layer 4 talks to layer 3, how layer 3 talks to layer 2, and so on.
So modularity, like Lego bricks. Different companies can make different bricks, but they all snap together because the connection points are standard.
That's a perfect analogy. It promotes interoperability. Different technologies from different vendors can work together, and it massively simplifies troubleshooting. If your email isn't working, you can narrow down which layer might be the problem rather than needing to understand the entire internet stack.
Makes sense. So the most famous conceptual model is the OSI model, Open Systems Interconnection, 7 layers.
That's the one, developed by ISO. It's more of a theoretical framework, a teaching tool, really, but it's fundamental for understanding network functions. It provides a great mental map.
Okay, let's try to make it concrete. The sources use a package delivery analogy. Can we walk through that? Sending a package layer by layer.
Sure. Imagine you're sending something complex. You start at the top, layer 7, the application layer. You, the user, are interacting with your software, writing an email, browsing a website, preparing the actual content.
Okay, I've written my email. What's next? Layer 6.
Layer 6, the presentation layer. Your email content gets formatted. Maybe it's compressed to save space or encrypted for security using something like SSL TLS. It ensures the recipient's application can actually understand the format. It's the translator and packer.
Got it. Formatted, maybe secured. Then?
Layer 5, the session layer. This sets up the communication link. It's like calling the recipient or the courier service first to say, hey, I'm sending something, are you ready? It establishes, manages, and eventually terminates the connection or session between the two applications.
Makes sense, like logging into a website that starts a session.
Exactly. And keeping you logged in, managing your shopping cart, that's session management. Authentication and authorization also happen here, verifying who you are and what you're allowed to do in that session.
Okay, session established, now the actual data moving. Layer 4.
Layer 4, the transport layer. This is huge. Your potentially large email is broken down into smaller pieces called segments. Each segment gets labeled where it came from, source port where it's going, destination port, and a sequence number so it can be put back together correctly.
Ah, ports. We need to talk more about those. So this layer breaks it up and labels it for reassembly. Does it also ensure it gets there reliably?
Yes, for some protocols. This layer handles reliability, flow control, making sure the sender doesn't overwhelm the receiver, and error control, checking for and potentially correcting errors. It adds a checksum for integrity.
Like a quality control check for each piece. Okay, broken down, labeled, checked. Where next?
Layer 3, the network layer. This is the global addressing and routing layer. Each segment gets wrapped in a packet, and that packet gets the source and destination IP addresses, the global street addresses on the internet. Routers use these IP addresses to figure out the best path across multiple networks to get the packet to its destination network.
So transport layer is about getting data between applications reliably. Network layer is about getting packets between networks.
Precisely. Logical addressing and routing across the wider internet.
Almost there. Layer 2.
Layer 2, the data link layer. Now we're focused on the local part of the journey, getting the packet from one device to the very next device on the same local network segment, like from your computer to your home router. It takes the IP packet, puts it into a frame, and adds the physical addresses, the MAC addresses of the next immediate hop. It also handles error detection and flow control specifically for that single link.
MAC addresses, like the device's unique serial number for the local network.
Kinda, yeah. A unique hardware identifier for the network card within that local network. We'll dive into MSEs and how they relate to IP soon.
Okay, local delivery sorted. Finally, layer 1.
Layer 1, the physical layer. This is the actual hardware. The cables, copper, fiber optic, or the airwaves for Wi-Fi. It takes the frame from layer 2, which is just bits dialed in ones, and converts those bits into physical signals, electrical pulses, light flashes, radio waves, and transmits them over the medium. Now, on the receiving end, it converts those signals back into bits, pure physics and electronics.
Wow. Okay, that's the journey down. And the receiver just reverses the process, unpacking layer by layer back up to the application.
Exactly. Each layer on the receiving side undoes what its counterpart did on the sending side, checking addresses, checksums, reassembling segments, decrypting, decompressing, until the original data reaches the destination application.
That framework is incredibly helpful. Let's dive deeper into each layer now, maybe starting back at the top with the application layer, layer 7. This is where we live, right? Browsers, Email.
Yep. It's the layer closest to the user. All the software you interact with that needs the network. Chrome, Firefox, WhatsApp, Gmail, Outlook, Skype, game clients, you name it. It provides the interface for applications to access network services.
And the key protocols here are things like HTTP for the web.
Correct. HTTP, Hypertext Transfer Protocol, is fundamental for web browsing.
Yep.
FTP, File Transfer Protocol, for moving files around. SMTP, Simple Mail Transfer Protocol, for sending email. DNS, the domain name system, which is like the internet's phone book, translating names like google.com into IP addresses. Even older ones like Telnet for remote terminal access.
Most of these use a client-server model. My browser is the client, Google's website is the server.
That's the most common model, yes. The client sends a request, show me this web page, and the server sends a response. Here's the HTML. You can even see this with a simple ping command in your terminal. Your machine client sends an echo request packet. The server sends an echo reply. It shows packet sequence numbers and round-trip time, too.
Okay, but you mentioned ports earlier at the transport layer. They identify the application, right?
Yeah.
How does that work with the application layer?
Good connection. So your computer might have one IP address. That's its street address. But if you're running multiple applications, browser, email, chat, how does data coming in know which application to go to? That's where ports come in. They're like apartment numbers within the building, your computer.
So the IP address gets the packet to the right computer, and the port number gets the data inside that packet to the right application on that computer.
Exactly. Ports are 16-bit numbers, so there are about 65,000 possibilities. Some are reserved. These are the well-known ports: 01023, like port 80 for HTTP, port 443 for HTTPS, secure web, port 25 for SMTP. These are standardized.
So everyone knows where to find the web server service, metaphorically speaking.
Right. Then you have registered ports, 1024, 49151, for specific applications that aren't quite as universal, but have registered their standard port, like MySQL databases often use 3306, MongoDB uses 27017.
And the rest?
Those are ephemeral ports, 49152, 65535. Your computer picks one of these randomly when it initiates a connection as a client. So when your browser connects to google.com on port 443, Google server sends the reply back to your IP address and the specific ephemeral port your browser grabbed for that session. Once the connection closes, the port is freed up.
Clever. Ensures data goes exactly where it needs to, even with multiple things running.
It's essential for multitasking. Now, besides client-server, there's also peer-to-peer, PDP architecture.
Like BitTorrent.
That's the classic example. Devices connect directly to each other, acting as both client and server.
Yeah.
You download bits from others, you upload bits to others, no central server controlling everything.
What are the advantages of P2P?
It scales really well.
Yeah.
The more people join, the more resources, upload bandwidth, become available. It's decentralized, making it resilient, often used for file sharing, sometimes in university networks.
And for the huge players, like Googles and Facebooks, they use data centers.
Massive data centers, huge buildings packed with thousands, even hundreds of thousands of servers. They need extremely high availability, uptime static, predictable IP addresses, and enormous amounts of bandwidth, especially upload speed, to serve billions of users.
Makes sense. Okay, down to layer 6. Presentation layer. What was its job again? Formatting.
Formatting, translation, and security. It handles the syntax and semantics of the data, making sure the application on the other end can actually understand the data being sent.
So like converting text encoding ASCII to something else.
Exactly. Translation is one key function. Another is encryption, decryption. When you see that padlock in your browser, HTTPS, the SSL/TLS encryption that secures your data is often considered part of the presentation layer's role. It scrambles the data so eavesdroppers can't read it.
And compression, making files smaller.
Yep, compression too. Reducing the amount of data that needs to be sent, which saves bandwidth and speeds things up. It could be lossless, like for text files where every bit must be preserved, or lossy, like for images or video where you can lose a little detail without noticing much. This layer assumes the layers below will handle the actual transmission. It just prepares the data.
Got it. Layer 5, session layer, managing the conversation.
Precisely. Establishing, managing, and terminating the communication sessions between applications. Think of it as the dialogue coordinator.
Like when I log into Amazon, that starts a session.
Perfect example. Logging in establishes a session. This layer helps maintain that session as you browse different pages, keeps your shopping cart contents associated with you, and handles logging you out, terminating the session. It deals with synchronization too, making sure both ends of the conversation are on the same page, perhaps using checkpoints in long data transfers.
And authentication, proving who you are with username, password, and authorization, what you're allowed to do once logged in, happen here too.
They are tightly integrated with session management, yes. It ensures the dialogue is happening between the right parties and they have the right permissions.
Okay, now the big one. Layer 4, transport layer. End-to-end communication between applications, reliability.
This is where a lot of the magic happens for reliable data transfer. First, it takes the data stream from the session layer and performs segmentation. It breaks it into smaller chunks, the segments.
And adds those port numbers and sequence numbers we talked about?
Yes. Source port, destination port to identify the apps, and a sequence number to reassemble the data in the correct order at the other end.
What about flow control? Preventing overload?
Crucial. If the sender is much faster than the receiver, it could flood the receiver with data. Flow control mechanisms, like windowing, allow the receiver to tell the sender, hey, slow down a bit, I'm falling behind, ensuring smooth data flow without dropping packets because the receiver's buffer is full.
And error control, detecting mistakes.
Yes. Each segment gets a checksum calculated based on its content. The receiver recalculates the checksum. If they don't match, the segment is corrupted. Reliable protocols like TCP will then trigger a retransmission. It also uses sequence numbers and acknowledgement numbers to detect lost packets and handle duplicate packets, ensuring data arrives correctly and in order.
This is where TCP and UDP live, right? The two main protocols.
The two giants of the transport layer.
Yep.
Let's start with TCP, Transmission Control Protocol. It's connection-oriented.
Meaning it sets up a connection first?
Exactly. It uses a famous three-way handshake. The client sends a SYN, synchronized packet. The server replies with a SYN ACK, synchronize acknowledge. The client sends back an ACK, acknowledge. Only then does data transfer begin. This ensures both sides are ready and agree on starting sequence numbers, which are randomized for security.
So it's like a formal introduction before the conversation starts.
A very reliable one. TCP guarantees ordered, error-free delivery. It uses acknowledgements, ACKs, for received data and retransmits lost or corrupted segments. It has higher overhead because of all this management, but it's accurate.
Perfect for things where you need every bit right. File transfers, email, loading a web page.
Absolutely. Anything where data integrity is paramount, HTTP relies on TCP. Also, TCP connections are typically between just two endpoints.
Okay, what about UDP, User Datagram Protocol?
UDP is the opposite in many ways. It's connectionless, no handshake. It just sends the data segments, called datagrams in UDP.
I like sending postcards versus registered mail.
That's a great analogy. UDP is like postcards. You just drop them in the mail. They might get lost, arrive out of order, or be duplicated. It's best effort delivery.
Why would anyone use that? It sounds unreliable.
Because it's fast. Very low overhead. No connection setup, no acknowledgements, no retransmission management at the UDP layer itself. It's ideal for applications where speed is critical and losing a little data is acceptable.
Like what?
Real-time video conferencing, a drop frame is better than lag. Online gaming, speed is everything. DNS lookups, quick request response. UDP still uses checksums for error detection, mind you, but it doesn't correct errors by retransmitting. The application layer above it might handle that if needed.
Makes sense. Speed versus reliability trade-off. What about multiplexing, demultiplexing?
That's how you can run multiple network applications simultaneously on one computer using one network connection. Multiplexing at the sender takes data streams from different applications, your browser, your email, your game, and interleaves their segments into a single stream of packets going out. Demultiplexing at the receiver looks at the destination port number in each incoming segment and directs it to the correct application. Those port numbers are the key.
So I can stream music while browsing the web because multiplexing bundles it all together, and demultiplexing sorts it out at the other end based on ports.
You got it. Finally, this layer also deals with network-wide issues. Congestion control and QoS, quality of service.
Congestion, like a traffic jam on the internet.
Pretty much. When too much data tries to go through a part of the network, routers get overwhelmed, packets get dropped, delays increase. Congestion control mechanisms, built into TCP, for example, try to detect congestion and throttle back the sending rate to prevent the network from collapsing. It monitors traffic, regulates sending rates, sometimes called traffic shaping, and uses signals like ECN, explicit congestion notification, to tell senders to slow down.
And QoS, quality of service.
QoS is about providing different levels of service for different types of traffic. Think of it like HOV lanes or ambulance priority on a highway. It classifies traffic, e.g. voice call versus file download, prioritizes the important stuff, like the voice call, reserves resources, like bandwidth if needed, and shapes or polices traffic to enforce these priorities. It ensures critical apps work well even when the network is busy.
Super important for things like VoIP or video calls. Okay, layer 3, network layer. Global addressing and routing. IP addresses live here.
Correct. This layer handles logical addressing. It takes segments from the transport layer and adds source and destination IP addresses, creating an IP packet. These are the addresses that uniquely identify devices across the entire internet.
Then routing, finding the path.
Yes. Routers operate at this layer. They look at the destination IP address on an incoming packet and consult their routing tables to decide which outgoing path is the best next hop to get the packet closer to its final destination. It's like the internet's GPS system.
Routing tables. Are they just lists of destinations and paths?
Essentially, yes. They contain information about network destinations and the next router to send packets to reach them. These tables can be built statically, manually configured by an admin, or dynamically.
Dynamic sounds better, more adaptive.
Usually, yes. Dynamic routing uses protocols where routers talk to each other and automatically learn about network topology changes, like links going down or new paths becoming available, and update their tables accordingly. They use algorithms to find the optimal paths.
Like the distance vector routing mentioned in the sources?
That's a classic dynamic routing algorithm family. The basic idea is that each router maintains a table of distances, like number of hops, to all known networks. Periodically, it shares this table with its direct neighbors. When a router receives a table from a neighbor, it updates its own table if the neighbor reported a shorter path to a destination. It's like asking your neighbors, how far is town X from you, and updating your own map if they know a shortcut. This allows routing information to propagate through the network.
Clever. And to make routing efficient, IP address blocks are assigned regionally.
Yes, large blocks are assigned to ISPs and organizations geographically by bodies like IETF regional registries. This helps aggregate routes and keeps routing tables manageable, minimizing hops.
Okay, let's talk IP itself. IPv4 is the one most people know, like 192.168.0.1.
That's the one. Internet Protocol version 4 uses 32-bit addresses written as 4 decimal numbers separated by dots. Each address has a network portion, identifying the network, and a host portion, identifying the specific device on that network.
How do you know which part is network and which is host?
That's where the subnet mask comes in. It's another 32-bit number, like 255.255.255.0, used alongside the IP address. The 255 parts correspond to the network portion of the IP, and the 0 part corresponds to the host portion. It lets devices quickly determine if another IP address is on the same local network or on a remote network requiring a router.
And there are different classes, A, B, C, and private versus public IPs.
Historically, yes. Classes A, B, and C define default network host boundaries, though we now use CIDR, classless interdomain routing, and VLSM, variable length subnet masking, for more flexibility. And yes, private IP ranges, like 10.x.x, 172.16.x, x 172.31.x.x, 192.168.x, are reserved for internal use within organizations and homes. They aren't routed on the public internet. Public IPs are globally unique and assigned by ISPs.
What about special addresses, like 127.0.0.1?
That's the local host or loopback address. It always refers to the device itself. Useful for testing network services running on your own machine without actually sending packets out onto the network.
And an IPv4 packet itself has a specific structure, with TTL.
Yes. The IPv4 header contains fields like version, length, identification for fragmentation, flags, protocol number telling it what's inside, like TCP or UDP, header checksum, source and destination IPs, and importantly, time to live, TTL.
TTL prevents infinite loops, right?
Exactly. It's an 8-bit counter. Every time a router processes the packet, it decrements the TTL. If TTL reaches 0 before the packet arrives, the router discards it and usually sends an error message back. Stops lost packets from circling forever and clogging the network.
But we ran out of IPv4 addresses, basically, which leads to IPv6.
We did, or it came very close.
Yeah.
IPv4 has about 4.3 billion addresses, which sounds like a lot, but wasn't enough for the internet's growth. IPv6 is the successor designed to solve this. It uses 128-bit addresses.
128 bits. How many addresses is that?
An astronomical number, roughly 340 undecillion, 3.4 by 1038, enough for every grain of sand on Earth to have trillions of IP addresses. Address exhaustion is not a problem with IPv6.
Wow. What else is different about IPv6?
It uses hexadecimal notation, like 2001.0db8.A2E.0373.7334. It has a simpler header structure for faster processing by routers. It has built-in support for things like SLAE, stateless address auto-configuration, allowing devices to configure their own addresses more easily. Better support for mobility and QoS. And crucially, IPsec, the security protocol suite, is mandatory, making it inherently more secure.
Is it backward compatible with IPv4?
Not directly, unfortunately. That's where the transition has been slow and complex. We need mechanisms like tunneling and dual-stack networks where devices run both IPv4 and IPv6 simultaneously during the transition period.
Okay, back to the network layer. We also have middle boxes interacting with IKEY packets, like firewalls.
Right. Firewalls sit at network boundaries and inspect packets, deciding whether to allow them through based on rules. These rules can look at source destination IP, ports, protocol type, even flags in the packet header, like blocking incoming packets with the SYN flag set or try to initiate a new connection.
Stateful versus stateless firewalls.
A stateless firewall examines each packet independently, without knowing about past packets. A stateful firewall keeps track of active connections, maintains state in a cache. If it sees a SYN packet going out, it knows to expect a SYN ACK coming back for that connection and will allow it. This is generally more secure and efficient.
And NAT, network address translation, that helps with the IPv4 address shortage too, right?
Massively. NAT allows a whole private network, using private IPs, to share a single public IP address when accessing the internet. When a packet goes out from a private device, the NAT device, often your home router, replaces the private source IP with its own public IP and remembers the mapping. When the response comes back to the public IP, NAT looks up the mapping and forwards the packet to the correct private device. It modifies the IP header, address checks them on the fly.
Like a receptionist handling mail for an entire office building using one public address.
Perfect analogy. It conserves public IPs and adds a layer of security by hiding the internal network structure.
Okay, down to layer 2, data link layer. Local delivery, frames, MAC addresses. What are the key responsibilities here? This seems important for exams.
Definitely. Key responsibilities include physical addressing, using those MAC media access control addresses. These are 48-bit, 6-byte, unique hardware identifiers burned into every network interface card, NIC, by the manufacturer, globally unique. Written in hexadecimal like 0.1.2b.3c.40.5e. A device can have multiple MACs, one for Ethernet, one for Wi-Fi, one for Bluetooth. MACs are used for addressing within the same local network segment.
So IP gets the packet to the right network, MAC gets the frame to the right device on that specific network.
Precisely, which leads to the next responsibility, Address Resolution Protocol, ARP. How does your computer find the MAC address of another device on the local network when it only knows its IP address? It uses ARP.
How does ARP work? Does it shout?
Kind of. Your computer first checks its local ARP cache, a temporary table of recent IP to MAC mappings. If the mapping isn't there, it broadcasts an ARP request packet to everyone on the local network, saying, who has IP address 192.168.1.5? Tell me, my IP, and MAC, your MAC address. The device with that IP address sends an ARP reply directly back saying, that's me, here's my MAC. The sender then caches this mapping and can send the frame directly.
And RARP, reverse ARP.
Oh, the opposite.
Yeah.
Finds an IP address given an AMP address. Less common now, mostly replaced by DHCP, but historically used by diskless workstations to get their IP when booting up.
DHCP, Dynamic Host Configuration Protocol. That's layer 2 as well. I thought it gave out IP addresses, layer 3.
Good question. DHCP assigns layer 3 information, IP address, subnet mask, gateway IP, DNS server IPs. But the protocol itself operates typically using broadcasts at layer 2 to find a DHCP server and negotiate the lease before the client has a configured IP address, so it bridges the layers functionally. It simplifies network management hugely by automatically assigning IPs from a pool.
What other responsibilities does layer 2 have? Flow control, error detection again?
Yes, but specifically for the point-to-point link between adjacent nodes. Flow control mechanisms prevent one device from overwhelming its immediate neighbor on the link. And error detection, usually via a frame check sequence, FCS, added to the end of the frame, allows the receiver to detect if the frame got corrupted during transmission across that single link. If an error is detected, the frame is typically just dropped. Higher layers, like TCP, might handle retransmission if needed.
The sources mention specific flow control protocols like stop and wait, sliding window, and piggybacking.
Right. These are data link layer techniques. Stop and wait is simple. Send one frame, wait for an ACK before sending the next. Inefficient. Sliding window protocols allow the sender to transmit multiple frames up to a certain window size before needing an ACK, improving efficiency. Piggybacking is an optimization where the ACK for received data is piggybacked onto an outgoing data frame heading back to the original sender, saving bandwidth by not needing separate ACK frames.
And managing access to the network medium. Multiple access protocols.
Crucial, especially when the medium is shared, like old bus networks or modern Wi-Fi. How do multiple devices avoid transmitting at the exact same time and garbling each other's signals? A collision.
Like Aloha, just transmit and hope.
Aloha was an early one from Hawaii. Pure Aloha. Transmit whenever you want. If a collision happens, detected by lack of ACK, wait a random time and try again. Slotted Aloha improved it slightly by only allowing transmissions at the start of time slots, still prone to collisions.
Then came CSMSD for Ethernet. Carrier sense multiple access with collision detection.
The classic Ethernet mechanism, carrier sense, CS. Listen before transmitting. If the medium is busy, wait. Multiple access, MA. Multiple devices share the medium, collision detection, CD. While transmitting, also listen. If you detect another signal interfering with yours, a collision, stop transmitting immediately, send a jam signal to ensure everyone knows the collision happened, wait a random back-off period using an exponential back-off algorithm, and then try again, starting with carrier sense. Much more efficient than Aloha for wired LANs.
Speaking of Ethernet, it has a specific frame format.
Yes, the Ethernet frame structure is key. Starts with the preamble and start frame delimiter, SFD, alternating ones and hours used for clock synchronization. Then the destination MASI address, 6 bytes, and source MAS address, 6 bytes. Then a length type field, 2 bytes, indicating either the length of the data field or the layer 3 protocol carried inside, for example, IPv4, IPv6. Then the data payload itself, the IT packet, typically 46 to 1500 bytes. And finally, the frame check sequence, FCS, 4 bytes. A CRC checksum calculated over the addresses, type, and data fields for error detection.
Very structured. Okay, lowest level. Layer 1, physical layer. Bits, signals, cables, hardware.
The raw transmission. Converting the ones and layers of the frame into physical energy, electrical voltages on copper wire, pulses of light in fiber optic cable, radio waves through the air, and doing the reverse at the receiver. It defines the physical characteristics of the connection. Voltage levels, timing, data rates, physical connectors, like RJ45 for Ethernet, cable specifications.
We have guided media versus unguided media here.
Right. Guided media provides a physical path. Twisted pair cables, like Cat5, Cat6 used for Ethernet, are common, inexpensive. Coaxial cable, like for cable TV internet, offers better shielding and bandwidth than older twisted pair. Fiber optic cable uses light pulses, offering huge bandwidth, long distances, and immunity to electrical interference. It's the backbone of the internet, including those vital transoceanic submarine cables connecting continents much faster and higher capacity than satellites for point-to-point links.
And unguided media, through the air.
Yep. Radio waves, Wi-Fi, Bluetooth, cellular, 3G, 4G, 5G, microwaves, point-to-point terrestrial links, satellite communications, infrared, short-range line of sight, like TV remotes, offers mobility, but is susceptible to interference and security issues.
What about network connecting devices? Where do they fit in the layers?
Good question. Often tested. Repeater. Operates at the physical layer, layer 1. Just regenerates the electrical or optical signal to extend distance. Doesn't understand frames or packets. Typically 2 ports. Hub. Also physical layer, layer 1. Essentially a multi-port repeater. Any signal coming in one port is regenerated and sent out all other ports, creates a single collision domain, inefficient.bridge. Operates at the data link layer, layer 2. Smarter than a hub. Learns which end-mount addresses are on which port, segment, only forwards frames, destined for another segment. Filters traffic based on MAS, separates collision domains, typically 2 to 4 ports, switch. Also data link layer, layer 2. Basically a fast multi-port bridge. Uses dedicated hardware, ASICs, to learn MC addresses and forward frames only out the specific port needed for the destination MAC. Each port is often its own collision domain. The foundation of modern LANs.router operates at the network layer, layer 3, connects different networks, different IP subnets, makes forwarding decisions based on IP addresses using routing tables, separates broadcast domains, essential for internet communication. Gateway, a broader term, often operates at multiple layers, including application, layer 7. Connects networks with different protocols or architectures, performing translation between them, e.g., connecting an IP network to an old mainframe network, or acting as an email gateway. Router, a historical device combining bridge, layer 2, and router, layer 3 functions. Could route routable protocols like IP and bridge non-routable ones. Less common now as switches and routers handle these functions better.
That clarifies where each device works. Now, is there a theoretical limit to how fast data can be sent? The sources mention Shannon's law.
Ah, yes, the Shannon-Hartley theorem. It's a fundamental concept from information theory. It defines the theoretical maximum data rate, a channel capacity C, you can achieve over a communication channel with a certain bandwidth, B, measured in hertz, and a given signal-to-noise ratio, SNO. The formula is C log 2 1 plus SN.
So capacity depends on how wide the pipe is, bandwidth, and how clean the signal is relative to the background noise.
Exactly. It tells us there's a hard physical limit. You can't just keep pushing data faster indefinitely on a given channel. To increase capacity, you need either more bandwidth or a cleaner signal. Less noise, more power. It sets the ultimate speed limit for any communication system based on physics.
Fascinating. Okay, we spent a lot of time on the 7-layer OSI model, but the TCP/IP model is more practical for the real internet.
Yes, the TCP/IP model, also called the Internet Protocol Suite, is the descriptive model that more closely reflects the actual protocols used on the internet. It's typically shown with 4 layers, sometimes 5.
How does it map to OSI?
Roughly, TCP/IP's application layer combines OSI's application, presentation, and session layers. It covers protocols like HTTP, SMTP, DNS.
Yeah.
TCP/IP's transport layer maps directly to OSI's transport layer, TCP/UDP. TCP/IP's internet layer maps to OSI's network layer, IP routing protocols.
Yeah.
TCP/IP's network interface layer, or link layer, combines OSI's data link and physical layers, Ethernet, Wi-Fi, drivers, cables. Sometimes this is split into data link and physical in a 5-layer TCP/IP model.
So fewer layers, more focused on the core internet protocols. OSI is good for learning concepts. TCP/IP describes the reality.
That's a good way to put it. TCP/IP evolved organically with the internet itself. It's the practical implementation.
Let's revisit some key application layer protocols in more detail. www and HTTP, the web.
The World Wide Web, WWW, isn't the internet itself, but a service on the internet. It's a vast collection of interlinked documents, web pages, and resources, images, videos, hosted on web servers worldwide, identified by URLs, Uniform Resource Locators.
And HTTP, Hypertext Transfer Protocol, is the protocol used to request and deliver those resources.
Correct. It's a client-server protocol. Your browser, client, sends an HTTP request to a web server. The server processes it and sends back an HTTP response, usually containing the requested resource, like an HTML page.
Requests have methods like GET and POST?
Yes. GET is used to retrieve data, e.g. fetch a web page. POST is used to submit data to the server, e.g. submit a login form, upload a file. Others include PUT, update a resource, and delete, you move a resource.
And responses have status codes, like 404.
Right. They tell the client the outcome. 2XX codes mean success. For example, 3XX mean redirection. Example, 301 move permanently. 4XX mean client error. EJ 404 not found. 403 forbidden. 5XX means server error. EJ 500 internal server error.
HTTP is stateless, meaning the server forgets about the client after each request.
By default, yes. Each request is independent. To maintain state across multiple requests, like keeping you logged in or remembered your shopping cart, cookies are used.
Ah, cookies. Small bits of data the server asks the browser to store.
Exactly. The server sends a cookie with a response, the browser stores it, and sends it back with subsequent requests to the same server. This allows the server to recognize the user and maintain session information. We distinguish between first-party cookies from the site you're visiting and third-party cookies from other domains, often advertisers or trackers embedded on the page.
Got it. Next key protocol, DNS, Domain Name System, the Internet's phone book.
Absolutely critical. Translates human-friendly domain names, www.google.com, into computer-friendly numerical IP addresses, 142.250.187.164. Without it, browsing would be impossible unless you memorized IP addresses.
And it's a distributed hierarchical database, not one giant central book.
Crucial design choice. A central DNS would be a massive bottleneck and single point of failure. Instead, it's hierarchical. At the top is the root domain. Below that are top-level domains, TLDs like .com, .org, .net, country codes, .uk, .de, .jp. These are managed by organizations overseen by Iron Internet Corporation for assigned names and numbers.
Below TLDs are the names we actually register, like Google and Google.com.
Yes, those are second-level domains. You can have further subdomains like mail.google.com or news.google.com. A complete name like www.google.com is a fully qualified domain name, FQADN.
So how does the lookup actually work, the DNS resolution process?
It's a multi-step query, usually very fast. 1. Your computer checks its local DNS cache. 2. If not found, it asks its configured local DNS server, often provided by your ISP. 3. If the local server doesn't know, and it's not cached, it starts querying up the hierarchy. It asks a root DNS server, where can I find info about .com? 4. The root server replies with the IP address of a .com TLD server. 5. The local server then asks the TLD server, where can I find info about google.com? 6. The TLD server replies with the IP address of the authoritative name server for google.com. run by Google. 7, finally, the local server asks Google's authoritative server, what's the IP address for www.google.com? 8, the authoritative server responds with the IP addresses. 9, the local server sends the IP back to your computer and caches it for future use.
Wow, quite a chain reaction, but happens in milliseconds. And we rent domain names, not buy them.
Correct. You register a domain name through a registrar, like GoDaddy, Namecheap, for a periodic fee. The registrar pays fees to the registry managing the TLD, like VeriSign for .com and ICANN.
Okay, let's talk email architecture. Lots of moving parts.
Indeed. You have user agents, UAs, your email client software, Outlook, Thunderbird, Mail app, or webmail interface, Gmail. You have mail transfer agents, MTAs, the mail servers like Postfix Exchange, that relay email between servers using SMTP. You have mail delivery agents, MDAs, that place incoming email into the user's mailbox on the server. And protocols, SMTP for sending, POP3 IMAVA for receiving. DNS is vital too, specifically MX, Mail Exchanger Records, which tells sending MTAs which server handles email for a given domain, plus spam filters, security layers.
So SMTP, Simple Mail Transfer Protocol, is purely for sending mail, server to server or client to server.
Both. Your UA sends the outgoing email to your organization's or ISP's SMTP server using SMTP. That server then uses SMTP to relay the message to the recipient's SMTP server, finding it via the MX record. It uses TCP, usually port 25, for reliable delivery.
And for receiving email, we use POP3 or IMAP.
Correct. These are protocols your user agent uses to retrieve mail from your mailbox on the mail server.
What's the difference, POP3 Post Office Protocol 3?
POP3 is simpler. Your client connects, authenticates, downloads new messages to your local device, and typically deletes them from the server, though it can be configured not to. It's like emptying your physical mailbox. Mail isn't easily synced across multiple devices.
And IMP, Internet Message Access Protocol.
IMAP is more modern and flexible. It keeps the emails on the server. Your client connects, authenticates, and syncs with the server, showing you the messages in folders stored there. You can organize mail into folders, access it from multiple devices, phone, laptop, web, and changes made on one device, like reading or deleting an email, are reflected everywhere because the master copy stays on the server until you explicitly delete it. It's much better for multi-device access.
Makes sense why IMP is more common now. Let's switch gears to error detection and correction. Why do we need this? Things go wrong in transit.
Absolutely. Noise, interference, faulty hardware, lots of things can flip bits during transmission. We need ways to detect these errors and ideally correct them.
How do we detect them? Block coding and checksums.
Those are common techniques. Block coding involves adding redundant bits, parity bits, to blocks of data in a structured way so the receiver can check for consistency. A simple example is adding a single parity bit that makes the total number of ones in the block either even or odd. Checksums are more robust. A mathematical calculation is performed on the data block, and the result, the checksum, is appended. The receiver performs the same calculation. If the results don't match, an error occurred. TCP and UDP use checksums for detection. TCP uses acknowledgments and retransmissions for correction.
Can we actually correct errors without retransmission? The sources mention Hamming code.
Yes, some codes, like Hamming codes, are forward error correction, FEC codes. They add redundant bits so cleverly that the receiver can not only detect that a single bit error occurred, but also determine which bit flipped and correct it automatically. More complex codes can correct multiple bit errors. This is crucial where retransmission is impossible or too costly, like deep space communication or some real-time streams.
What about single bit versus burst errors?
A single bit error is just one bit flipped. A burst error means multiple consecutive bits are corrupted, often due to longer-lasting interference, like a noise spike or a scratch on a disk. Burst errors are generally harder to handle with simple codes like single parity bits or basic Hamming codes. More sophisticated techniques like interleaving or Reed-Solomon codes are often used to combat them.
Okay, let's revisit networking, media, and wireless technologies. We covered guided cables and unguided airwaves.
Right. Guided includes twisted pair, coax, and fiber optics. Unguided includes radio, microwave, infrared.
What about wireless LANs, WLANs, like Wi-Fi? What are their main advantages? That seems like a key point.
The huge advantage of WLANs based on 802.11 standards is flexibility and mobility. Users can connect to the network without physical cables, move around within the coverage area, office, home, campus, and easily add new devices without running new wires. It dramatically simplifies network access in many environments.
And transmitting digital over analog requires modulation techniques, converting zeros and ones into waves, like FSK, ASK, PSK.
Exactly. These are fundamental ways to encode digital data onto an analog carrier wave. FSK, frequency shift keying, Uses two different frequencies to represent 0 and 1. Think high pitch for 1, low pitch for 0. ASK, amplitude shift keying, varies the amplitude, strength, or height of the wave. Think loud for 1, quiet for 0. PSK, phase shift keying, varies the phase, the starting point of the wave cycle. Thinks shifting the wave forward or backward slightly to represent 1 or 0. PSK, phase shift keying. More complex schemes like QAM, quadrature amplitude modulation, combine ASK and PSK to encode multiple bits per symbol for higher data rates.
Got it. And Bluetooth, that's another short-range wireless tech. How is it structured?
Bluetooth also has layers. A radio layer for the physical 2.4 GHz transmission. A baseband layer managing the physical link, hopping between frequencies to avoid interference, handling basic error correction. Above that is L2CAP, Logical Link Control and Adaptation Protocol, which multiplexes data, handles segmentation reassembly, and QoS.
And then profiles for specific uses.
Yes, the upper layers include things like Service Discovery Protocol, to find out what other devices can do. RFCOMM emulates a serial port, and various profiles that define how specific applications work. HFP for hands-free calls, A2DP for stereo audio streaming, HID for keyboards, mice, etc. Bluetooth supports classic, higher speed, and Bluetooth low energy, BLE. Very low power for sensors, wearables. Security involves pairing with shared keys, encryption, and authentication.
Finally, let's touch on network security fundamentals, protecting the network and data.
Essential. It's about ensuring confidentiality, preventing unauthorized disclosure, integrity, preventing unauthorized modification, and availability, ensuring legitimate access. The classic CIA triad.
Cryptography is key here. Symmetric versus asymmetric keys.
Two main types. Symmetric key cryptography, or secret key, uses the same key for both encryption and decryption. Algorithms like AES, Advanced Encryption Standard, are very fast and efficient, great for encrypting large amounts of data. The big challenge is key distribution. How do you securely share that secret key beforehand?
Old traditional ciphers like Caesar or Vigenère were symmetric but weak.
Yes, they use simple substitution or patterns easily broken with modern analysis. Useful for understanding crypto concepts, but not secure today.
So asymmetric key cryptography, or public key, solves the key distribution problem.
Largely, yes. It uses a pair of keys, a public key shared freely, and a private key kept secret. Anyone can use your public key to encrypt a message for you, but only you can decrypt it with your private key. Examples include RSA and ECC algorithms.
How is that used?
It's fundamental for secure key exchange, like in TLS SSL for HTTPS, use public key crypto to securely agree on a temporary symmetric key for the actual session data. Digital signatures, you encrypt a hash of a message with your private key. Anyone can verify it with your public key, proving you sent it and it wasn't tampered with. And generally secure communication without needing a pre-shared secret. It's slower than symmetric crypto, so often used for setup and signatures, while symmetric keys handle the bulk data.
Okay, we've covered a massive amount of ground. From ARPANET's origins through the OSI and TCP/IP layers, protocols like PCP, UDP, IPDNS, HTTP, the physical media, wireless tech, and security.
It really is an intricate ecosystem. Thinking back to that simple action, typing a URL, you now have a much better idea of the incredible journey that data takes. Segmented, packetized, routed across continents via cables and routers using MC addresses for local hops, all governed by protocols, checked for errors, maybe encrypted, and finally reassembled for your application.
Understanding these foundations isn't just academic, is it? It demystifies things, helps you troubleshoot, maybe even think about how to build the next generation of network tech.
Absolutely. It's about grasping the why and how. This deeper understanding empowers you. It moves you from just being a user to someone who truly comprehends the digital world's plumbing.
So a final thought for our listeners. As we move towards things like Web3, the metaverse, billions more IoT devices coming online demanding ever more speed, lower latency, and tighter security. How will these fundamental networking principles we've discussed, the layers, the protocols, the addressing, need to adapt or evolve?
That's the billion-dollar question, isn't it? Will the core ideas of layered architecture and protocols like TCP/IP hold, just with enhancements? Or will we see more radical shifts? How do we handle the scale, the security challenges, the real-time demands? Exploring those questions, building on this foundation, that's where the really fascinating insights lie.
Definitely something to ponder. Keep diving.